The Deep Ocean Facts, a journey to Earth's final frontier. Welcome, dear traveler, to a place of profound stillness and infinite mystery. Tonight, we journey together into the deepest reaches of our planet's oceans, where darkness reigns eternal and pressure becomes a physical force beyond human comprehension. Here, in these remote waters, life has found ways to flourish in conditions that would seem impossible to us surface dwellers. As you settle into comfort, breathing slowly and deeply, allow your mind to drift downward with me, past the sunlit shallows, through layers of dimming blue, into the vast unknown that covers more than 60% of our world. Let the gentle rhythm of these words carry you deeper, deeper still, into realms where the ordinary rules of existence transform into something altogether extraordinary. The deepest point, Mariana Trench and Challenger Deep. Imagine standing at the edge of the greatest canyon on Earth, not carved through rock and desert, but hidden beneath the vast Pacific Ocean. The Mariana Trench stretches like a crescent-shaped scar across the ocean floor, extending more than 1,580 miles in length and averaging about 43 miles in width. This geological wonder formed where two massive tectonic plates meet, the Pacific Plate slowly diving beneath the smaller Mariana Plate in a process that has continued for millions of years. The collision happens at such an infinitesimally slow pace that no human could ever perceive the movement. Yet over epochs of time, this patient grinding has created the deepest place accessible anywhere on our planet's surface. Within this already profound trench lies an even deeper depression, a place that represents the absolute extremity of depth on Earth. The Challenger Deep, named for the research vessels that first discovered and later confirmed its measurements, plunges to a depth that challenges our ability to comprehend. The most recent precise measurements place the bottom at approximately 10,984 meters below sea level, though various expeditions have recorded slightly different figures due to the immense technical challenges of measuring at such depths. To put this in perspective, if you could somehow lift Mount Everest from its base in the Himalayas and place it upside down into the Challenger Deep, the summit of the world's tallest mountain would still rest more than 7,000 feet beneath the ocean's surface, completely submerged in icy darkness. The discovery of this profound depth began in 1875 during the Challenger expedition, one of the first comprehensive scientific surveys of the ocean. Using a simple weighted rope dropped from their ship, researchers recorded a depth of 4,475 fathoms, approximately 8,184 meters. While impressive for its time, this measurement fell short of the true depth. It would take another 76 years before technology advanced sufficiently to reveal the full extent of the abyss. In 1951, the HMS Challenger II returned to the same general area, this time equipped with echo-sounding equipment that bounced sound waves off the seafloor and measured the time for their return. These readings revealed depths approaching 11,000 meters, finally exposing just how deep the trench truly descended. The physical act of reaching the bottom of the Challenger Deep represents one of the most extreme achievements in the history of human exploration. On January 23, 1960, Swiss oceanographer Jacques Piccard and United States Navy Lieutenant Don Walsh squeezed into the bathyscaphe Trieste, a specialized submersible designed to withstand crushing pressure. Their descent took nearly 5 hours as the vessel slowly dropped through complete darkness. When they finally touched down at a depth of 10,916 meters, they became the first humans to witness the absolute deepest point on Earth. The achievement was so difficult, so technically demanding, and required such specialized equipment that more than 50 years would pass before another person would make the journey. In March of 2012, filmmaker James Cameron designed and piloted the Deep-Sea Challenger submersible on a solo descent to the Challenger Deep, reaching a depth of 10,898 meters. Unlike Piccard and Walsh, who could only stay at the bottom for 20 minutes, Cameron spent 3 hours exploring, filming, and collecting samples from this alien environment. His vessel carried high-definition cameras and sophisticated lighting systems, though the extreme pressure took its toll on his equipment. Batteries drained faster than expected, sonar systems failed, and some of his thrusters malfunctioned, making maneuvering difficult. Despite these challenges, the footage he captured revealed a barren landscape of fine sediment, utterly devoid of the dramatic rock formations or exotic life forms that many had imagined. The most recent descents have been conducted by Victor Vescovo, who between 2019 and 2020 made multiple dives to various points in the Challenger Deep using the DSV limiting factor, a submersible specifically designed for repeated deep ocean exploration. On April 28, 2019, Vescovo reached a depth of 10,928 meters, setting a new record. What made his expeditions particularly valuable was that he brought scientists along on subsequent dives, allowing researchers to conduct real-time observations of the deep ocean environment. On one dive with Kelly Walsh, son of Don Walsh from the original Trieste expedition, they spent 4 hours exploring the western pool of the Challenger Deep at a depth of 10,923 meters, creating a symbolic connection between the early pioneers and modern exploration. The conditions at the bottom of the Challenger Deep exist at the very edge of what physics allows for liquid water. The pressure reaches approximately 1086 bar, or 15,750 pounds per square inch. To understand this force, imagine 8 tons of weight pressing down on every square inch of surface area. For a human body suddenly exposed to such pressure, the result would be instantaneous and catastrophic. Gas-filled spaces like lungs would collapse within microseconds, bones would crack and compress, and the body would be crushed into a fraction of its normal volume. Yet in this seemingly uninhabitable environment, life persists. The organisms that dwell here are so perfectly adapted to extreme pressure that bringing them to the surface causes their own set of problems. The rapid decrease in pressure as they ascend causes their cellular structures to fail, often resulting in death before they can be studied in detail. Temperature at these depths hovers just above freezing, typically between 1 and 4 degrees Celsius. The water remains liquid despite the cold because the immense pressure raises the freezing point. No sunlight has penetrated to these depths for millions of years. The darkness is absolute, complete, a blackness so total that human eyes would detect nothing whatsoever, even after hours of adjustment. This is not the darkness of a moonless night, where starlight still provides faint illumination. This is the darkness of a place that has never known light, where the concept of vision as we understand it becomes almost meaningless. The Mariana Trench formed approximately 50 million years ago through the process of subduction, where the ancient Pacific seafloor, some of the oldest oceanic crust on Earth at 170 million years old, slides beneath the younger Mariana Plate. As the denser, older crust descends into the Earth's mantle, it creates this profound depression in the seafloor. This same tectonic activity is indirectly responsible for the Mariana Islands themselves. A chain of volcanic islands formed as water trapped in the descending plate is released, causing the overlying mantle to melt and erupt at the surface. The trench continues to deepen incrementally with each passing year, though the change is far too small for any human instrument to detect over a single lifetime. Modern mapping of the trench using multi-beam sonar systems has revealed that its floor is not a smooth, featureless plain, but rather a complex landscape. With its own geography, rocky outcrops that were once seamounts poke up from the sediment. Smaller valleys and ridges create variations in depth across the trench floor. In some places, the sediment is thick and soft, accumulated over millions of years as dead organisms and particles rain down from above. In other areas, the rocky substrate lies exposed, scoured clean by deep ocean currents that flow even at these profound depths. The walls of the trench slope steeply, creating an environment where conventional anchors or sampling equipment often slide down into even greater depths, frustrating research efforts. The chemistry of the water changes with depth as well. Oxygen levels decrease, carbon dioxide concentrations increase, and the water becomes enriched with minerals dissolved from the crust. These chemical gradients create distinct habitats at different depths, each with its own suite of adapted organisms. Perhaps most sobering is the realization that even this most remote place on Earth shows evidence of human impact. Plastic debris has been found at the very bottom of the Challenger Deep. A plastic bag was photographed by Victor Vescovo during his 2019 dive, resting on sediment that took millennia to accumulate. Candy wrappers have been spotted. Microplastics have been detected in the tissues of amphipods collected from Hadal depths. Even more disturbing, analysis of organisms from the deepest parts of the ocean has revealed the presence of pollutants like polychlorinated biphenyls, industrial chemicals that were banned in the 1970s. These findings demonstrate that no part of the ocean, no matter how distant or inaccessible, remains untouched by human activity. The living darkness. Bioluminescence in the deep. As we drift deeper into the ocean's embrace, past the point where sunlight can penetrate, we enter a realm that is anything but dead. Though darkness surrounds us, this is not a world of complete blackness. Instead, it sparkles and shimmers with countless points of living light, as if the stars themselves had descended from the heavens and taken up residence in the depths. This phenomenon, called bioluminescence, represents one of nature's most enchanting adaptations to life. Bioluminescence is light produced by a living organism through a chemical reaction. At its core, the process involves a molecule called luciferin that reacts with oxygen in the presence of an enzyme called luciferase. This reaction produces light energy with almost no heat, making it far more efficient than any light bulb humans have ever created. The light is cold, pure, and serves purposes that are absolutely vital to survival in the lightless depths. What makes this adaptation even more remarkable is that it has evolved independently in the ocean more than 40 separate times, with different groups of organisms developing their own unique variations of the chemistry required to produce light. In the deep sea, bioluminescence is not rare or unusual. It is, in fact, the rule rather than the exception. Research conducted at the Monterey Bay Aquarium Research Institute revealed that approximately 3/4 of all animals living in the ocean's mid-water regions, from the surface down to 4,000 meters, possess the ability to create their own light. In certain groups, the prevalence is even higher. Nearly 100% of siphonophores, those delicate colonial organisms that can grow to more than 130 feet in length, are bioluminescent. More than 90% of deep-sea jellyfish, squid, and certain families of fish possess this ability. When we consider that the deep ocean represents the largest habitat on Earth by volume, bioluminescence may well be the most common form of communication on our entire planet. The colors of bioluminescence are not random, but are instead precisely tuned to the physics of underwater light transmission. The vast majority of deep-sea bioluminescence appears blue or blue-green, colors that correspond to wavelengths of light that travel farthest through seawater. Red light, with its longer wavelength, is absorbed within the first few meters of descent, which is why many deep-sea creatures are colored red. In an environment where no one can see red light, being red is effectively the same as being invisible. However, A few remarkable predators have evolved the ability to produce and see red bioluminescence, giving them a secret searchlight that illuminates their prey while remaining invisible to most other creatures. The stoplight loosejaw fish, for example, possesses organs beneath its eyes that produce red light, allowing it to hunt without alerting its victims to its presence. The purposes of bioluminescence in the deep ocean are as varied as the creatures that produce it. Many organisms use light to avoid being eaten, employing strategies of stunning sophistication. Consider the counter-illumination technique used by many small fish and squid. Predators looking upward from below see these creatures silhouetted against the faint glow that filters down from the surface. To break up this telltale silhouette, the prey animals have rows of light-producing organs called photophores arranged along their bellies. These photophores produce light that precisely matches the intensity and color of the downwelling surface light, effectively making the animals invisible when viewed from below. The system is so refined that special light sensors continuously monitor the brightness above and adjust the intensity of the bioluminescence to maintain perfect camouflage. Other creatures use bioluminescence as a burglar alarm, a desperate defense when escape seems impossible. When attacked, certain jellyfish, squid, and shrimp unleash brilliant displays of flashing lights designed to startle predators and attract even larger predators to the scene. The logic is simple but effective. If something is trying to eat you, light up the area and hope that your attacker becomes someone else's meal. Some species of deep-sea shrimp take this strategy to an extreme, vomiting bioluminescent fluid directly at their attackers. This glowing cloud acts like a smokescreen, confusing the predator and giving the shrimp precious seconds to escape into the darkness. The deep-sea anglerfish employs perhaps the most famous example of bioluminescence as a hunting tool. Female anglerfish possess a long, modified dorsal fin spine that extends forward above their mouths, tipped with a glowing lure called an esca. This lure doesn't produce light through the fish's own chemistry. Instead, it houses colonies of bioluminescent bacteria that the anglerfish cultivates in a specialized light organ. The fish provides nutrients and protection to the bacteria, and in return, the bacteria provide light that attracts curious prey directly toward the anglerfish's enormous, tooth-filled mouth. The lure can be flashed or waved to mimic the movements of small prey, an irresistible temptation for hungry fish in an environment where food is scarce. When an unsuspecting victim comes close enough to investigate, the anglerfish strikes with shocking speed, its jaws snapping shut in a fraction of a second. Flashlight fish have taken a different approach, carrying their own built-in headlamps. Beneath each eye, these fish have a large light organ filled with bioluminescent bacteria. The organ can be covered by a dark flap of skin, allowing the fish to turn its light on and off at will. Flashlight fish use this ability to illuminate potential prey items and coordinate movements with other members of their school, creating complex patterns of flashing lights in the darkness. The bacterial partnership is so successful that both organisms have become dependent on each other. The bacteria cannot survive outside the fish's light organ, and the fish relies on the light for hunting and social interaction. The bristlemouth, a small deep-sea fish with a large jaw packed full of needle-like teeth, holds the distinction of possibly being the most abundant vertebrate on Earth. Population estimates suggest there may be quadrillions of these fish in the ocean, far outnumbering every land animal combined. These tiny fish, rarely more than a few inches long, are covered in photophores that produce a constellation of lights along their bodies. The specific pattern of lights differs between species, likely serving as a recognition signal in the darkness. Imagine vast schools of these fish moving through the deep sea like living galaxies, each individual twinkling with its own points of light. Larger creatures also make use of bioluminescence, Certain species of sharks that dwell in the twilight zone have light-producing cells in their skin, allowing them to create a soft glow that matches the ambient light above. This provides the same counter-illumination camouflage that smaller fish use, rendering a 300-pound predator nearly invisible to prey looking up from below. Other deep-sea sharks use bioluminescence for communication, with patterns of glowing spots that may help individuals recognize members of their own species or advertise their presence to potential mates. The mechanisms by which different organisms produce light vary considerably. Some species, like the anglerfish and flashlight fish, form symbiotic relationships with bioluminescent bacteria. The bacteria do all the actual light production, while the host provides ideal living conditions. Other organisms produce light through their own cellular chemistry. They manufacture their own luciferin and luciferase, storing these chemicals in specialized organs or cells. When light is needed, the chemicals are mixed together, triggering the reaction. Some organisms can control the intensity and duration of their glow, while others produce a single bright flash and then must wait for their chemistry to reset before they can glow again. The evolution of bioluminescence represents one of the most successful adaptations in the history of life. In an environment where traditional vision would be useless, where food is scarce, and where every advantage matters for survival, the ability to produce light has become nearly universal. From the smallest bacteria to the largest squid, from simple jellyfish to complex fish, bioluminescence has transformed the darkness of the deep sea into a realm of wonder, a place where living light illuminates the eternal night. As we continue our journey downward, every direction we look reveals new sparkles, new flashes, new demonstrations of this remarkable adaptation, reminding us that even in Earth's darkest corners, life finds ways not merely to exist, but to shine. Oases of the abyss, hydrothermal vents deep beneath the waves, in places where sunlight has never reached, where the pressure could crush a submarine like a tin can. Life has discovered an entirely different way to exist. In 1970, scientists aboard the research submersible Alvin were exploring the Galapagos Rift, a section of the mid-ocean ridge in the eastern Pacific Ocean, when they noticed something strange in their temperature data. The water temperature was spiking dramatically, jumping from near freezing to levels far above what should be possible at such depths. Curious and excited, they followed these anomalies and made one of the most significant biological discoveries of the 20th century. They found hydrothermal vents. And surrounding these vents, thriving in conditions that had been thought completely hostile to life, they discovered an entire ecosystem unlike anything ever seen before. Hydrothermal vents form at places where tectonic plates are pulling apart, creating cracks and fissures in the Earth's crust. Cold seawater seeps down through these fractures, descending sometimes several kilometers into the crust, where it encounters extremely hot magma. The water is heated to temperatures exceeding 400 degrees Celsius, hot enough to melt lead. Under normal circumstances, water at this temperature would explosively boil into steam, but the tremendous pressure at these depths, often several hundred times atmospheric pressure, prevents boiling and keeps the water in liquid form. As this superheated water dissolves minerals from the surrounding rocks, it becomes a chemical-rich soup loaded with sulfur compounds, metals, and other elements. The heated, mineral-laden water becomes less dense than the surrounding cold water and begins rising back toward the sea floor, eventually erupting from the vents in billowing plumes. As the superheated vent fluid encounters the frigid ocean water, rapid chemical reactions occur. The dissolved minerals precipitate out of solution, forming solid particles that give the plumes their characteristic appearance. Black smokers, the most dramatic type of hydrothermal vent, emit plumes so dark they look like underwater tornadoes of ink. The black color comes from iron sulfide and other metal sulfides precipitating as the hot fluid hits cold water. These minerals build up around the vent opening, gradually constructing chimneys that can grow to heights of 18 stories or more, towering structures of mineral deposits that continue to grow as long as the vent remains active. White smokers, by contrast, emit paler plumes rich in lighter-colored minerals like barium, calcium, and silicon. These vents typically operate at slightly lower temperatures than black smokers, producing more delicate, ethereal plumes that drift upward through the darkness. The mere existence of hydrothermal vents would be fascinating enough from a geological perspective, but what truly amazed the scientist who first explored them was the abundance of life thriving in their immediate vicinity. The seafloor around hydrothermal vents hosts ecosystems with a biomass 10,000 to 100,000 times greater than the surrounding deep ocean. Giant tube worms, some reaching lengths of over 2 meters, cluster in dense groves around the vents, their brilliant red plumes swaying in the currents. These worms have no mouth, no digestive system, and no ability to eat in the conventional sense. Instead, they host colonies of bacteria inside their bodies, providing the bacteria with the raw materials needed for survival, while the bacteria produce nutrients that feed the worms. Clusters of enormous clams and mussels, some reaching 12 inches across, carpet the rocks near vents. Pale white crabs scuttle across the substrate, their bodies lacking the pigmentation found in their shallow water cousins because in perpetual darkness there is no evolutionary advantage to producing color. Blind shrimps swarm in thousands around some vents, their eyes evolved into useless stumps but their backs covered in heat-sensing organs that allow them to navigate the temperature gradients around the vents without getting so close that they cook. The shrimp graze on bacterial mats that cover the rocks, bacteria that thrive in conditions that would be instantly lethal to most other forms of life. The basis of these ecosystems is fundamentally different from every other ecosystem on Earth's surface. In forests, grasslands, coral reefs, and even the sunlit surface layers of the ocean, the foundation of life is photosynthesis, the process by which plants and algae use sunlight to convert carbon dioxide and water into sugars. But at hydrothermal vents, where no sunlight penetrates, photosynthesis is impossible. Instead, life relies on chemosynthesis, a process by which bacteria use the chemical energy from vent minerals, particularly hydrogen sulfide, to produce organic compounds. These bacteria form the base of the vent ecosystem's food web. Some species live freely in the water column, or as mats on the rocks, while others live symbiotically inside larger organisms like tube worms, clams, and shrimp. The bacteria convert the toxic chemicals spewing from the vents into usable energy, and the animals that host or consume these bacteria thrive in an environment that would otherwise provide no food whatsoever. This discovery forced scientists to completely reconsider their assumptions about the requirements for life. Before 1977, sunlight had been considered essential for any productive ecosystem. The deep ocean was thought to be dependent on a slow rain of organic debris drifting down from the sunlit surface layers, a meager food supply that could only support sparse populations of organisms with slow metabolisms. The hydrothermal vents proved that assumption wrong. Here was an ecosystem energized not by the sun, but by the heat of the Earth itself, sustained by chemical energy released from our planet's interior. If life could thrive in such extreme conditions on Earth, perhaps it could also exist in similar environments elsewhere in the solar system. Icy moons like Europa and Enceladus are thought to have liquid water oceans beneath their frozen surfaces, possibly warmed by tidal heating, and perhaps hosting their own hydrothermal vents. The discovery of chemosynthetic life on Earth has transformed these distant worlds from barren ice balls into potential habitats for life. The vent communities are not static, but rather dynamic environments that can appear and disappear on relatively short timescales. An active vent might persist for decades or even centuries, providing a stable environment for its resident organisms. But volcanic and tectonic activity can shut off a vent with little warning as magma shifts or new cracks form in the crust, diverting the flow of heated water elsewhere. When a vent dies, its ecosystem dies with it, unable to survive without the chemical energy that sustained them. However, new vents frequently form nearby, and the organisms that depend on them have evolved remarkable abilities to disperse across vast distances of barren seafloor, colonizing new vents soon after they become active. Larvae of vent species drift with deep ocean currents, sometimes traveling hundreds of miles before settling at a new vent site. Scientists studying fossils in ancient rocks have found evidence that hydrothermal vent ecosystems have existed for hundreds of millions of years, possibly billions. Some of the oldest fossils that might represent life on Earth, structures found in rocks nearly 4 billion years old in Canada, appear to have formed in hydrothermal vent environments. This has led to speculation that life itself might have originated at deep-sea hydrothermal vents. The chemical gradients around vents, with their abundance of reactive compounds and energy sources, could have provided ideal conditions for the complex organic molecules required for life to assemble themselves. The vents would also have offered protection from the frequent meteorite bombardments that struck early Earth's surface, allowing primitive life forms to evolve without being repeatedly sterilized by impacts. While this hypothesis remains controversial and alternative origin theories exist, the remarkable antiquity and unique chemistry of vent environments make them compelling candidates for the birthplace of life on our planet. Dozens of hydrothermal vent fields have now been discovered throughout the world's oceans, from the Arctic to the Antarctic, along the mid-ocean ridges that encircle the globe like the seams on a baseball. Each vent field has its own character, its own community of organisms, sometimes with species found nowhere else on Earth. The Cayman Trough in the Caribbean hosts the world's deepest known vents at depths approaching 5,000 meters. The vents of the Juan de Fuca Ridge off the coast of the Pacific Northwest have been studied extensively because they are relatively accessible. The vents of the Mid-Atlantic Ridge are notable for hosting the Lost City Hydrothermal Field, where white carbonate spires grow from the seafloor in formations that look like an underwater cathedral, supporting ecosystems based on different chemistry than typical black smoker vents. The minerals precipitating from hydrothermal vents don't just build chimneys and support ecosystems, they also contribute to ocean chemistry and may play roles in the formation of valuable ore deposits. The high concentrations of metals in vent fluids mean that some vent sites accumulate significant deposits of copper, zinc, gold, and other valuable minerals. This has led to interest in deep-sea mining, with some companies proposing to harvest these deposits. However, the ecological importance of vents and the fragility of their ecosystems have raised serious concerns about the impacts such mining might have. Destroying a vent field to extract minerals would obliterate ecosystems found nowhere else on Earth, potentially driving species to extinction before we even have a chance to study them. As we drift through the darkness past these remarkable oases of life, past the dancing shrimp and the swaying tube worms, past the plumes of mineral-rich water rising like smoke from chimneys of stone, we're reminded that our planet holds mysteries beyond imagination, that life is more adaptable, more creative, more persistent than we ever dared to suppose. Surviving the crush. Deep-sea adaptations. The deeper we descend, the more the very nature of existence transforms. At the surface, we live beneath a thin blanket of atmosphere that presses down with a force we rarely think about. 1 atmosphere of pressure, approximately 14.7 pounds per square inch. For every 10 meters we descend below the surface of the ocean, another atmosphere of pressure is added. At 100 meters depth, a diver experiences 10 atmospheres of pressure. At 2,000 meters, the pressure reaches 200 atmospheres. And at the bottom of the Challenger Deep, nearly 11,000 meters down, the pressure exceeds 1,080 atmospheres. The force is almost incomprehensible, equivalent to having 8 tons pressing down on every square inch of surface area. For humans and other air-breathing surface creatures, such pressure would be immediately fatal. Our bodies contain gas-filled spaces, primarily our lungs, that would be catastrophically compressed. Within seconds of exposure to deep ocean pressure, our lungs would collapse, our eardrums would rupture, nitrogen gas would be forced into our bloodstream, causing nitrogen narcosis, and our very bones would begin to crack and compress under the load. Yet, throughout the deep ocean, life flourishes. Fish swim, squid hunt, crustaceans scavenge, and jellyfish drift, all apparently unconcerned by pressures that would annihilate a human. How do they manage this seemingly impossible feat? The secret lies in a simple but elegant principle. Organisms that lack gas-filled spaces are far less affected by pressure than we imagine. Water is nearly incompressible, and most deep-sea creatures are largely made of water and other incompressible materials. Unlike humans with our air-filled lungs and sinuses, deep-sea fish typically lack swim bladders, the gas-filled organs that shallow water fish use to control their buoyancy. Instead, deep-sea fish maintain neutral buoyancy through other means. Some species have enlarged livers filled with low-density oils that provide lift without requiring compressible gas. Others have bones that are barely mineralized, more cartilage than true bone, reducing their overall density. Many deep-sea creatures appear soft, gelatinous, almost liquid in consistency, because this body plan simply works better under extreme pressure. Consider the blobfish, an animal that has become something of an internet sensation for its saggy, melancholic appearance. When pulled to the surface, a blobfish looks like a pile of pink slime, barely holding its shape. This appearance has made it the subject of countless memes, often being called the world's ugliest animal. But this perception is completely unfair, because what we're seeing is a creature that has been ripped from its natural high-pressure environment and subjected to conditions its body was never designed to withstand. At depth, with pressure supporting its gelatinous tissues, the blobfish has a more normal fish-like shape. Its soft body isn't a design flaw, but rather a sophisticated adaptation. The gel-like tissues compress under pressure without being damaged, allowing the fish to function normally at depths where rigid-bodied animals would struggle. The cellular-level adaptations of deep-sea life are equally remarkable. Under extreme pressure, the proteins and other molecules that make up living cells tend to distort and malfunction. Cell membranes, which need to maintain a specific balance between fluidity and rigidity to function, can become too rigid under high pressure, causing cells to fail. Deep-sea organisms have evolved specialized lipids in their cell membranes that remain properly fluid even under crushing pressure. They also accumulate high concentrations of a molecule called trimethylamine N-oxide, or TMAO. This organic compound has the remarkable property of stabilizing proteins and preventing them from being deformed by pressure. The deeper an organism lives, the higher the concentration of TMAO it maintains. Fish living at 3,000 feet below the surface have relatively low levels. The Hadal snailfish, found at depths exceeding 8,000 meters in the deepest trenches, has TMAO concentrations among the highest ever measured. Interestingly, TMAO is the same compound responsible for the characteristic fishy smell of fish. The more a fish is adapted to deep water, the more pronounced this smell becomes. But in its natural environment, deep beneath the surface, this smell is irrelevant. There, TMAO serves the vital function of maintaining protein structure under conditions that would otherwise cause molecules to fail. Research has shown that there appears to be a maximum depth limit for fish, somewhere around 8,500 meters, beyond which even TMAO cannot adequately protect cellular proteins from pressure damage. This depth limit explains why no true fish have been found in the deepest parts of the trenches, though other organisms like amphipods, sea cucumbers, and certain worms have been collected from the very bottom of the Challenger Deep, suggesting they have additional adaptations that allow them to function at even greater depths. For creatures that must traverse depth zones, moving from shallow to deep or vice versa, additional adaptations are necessary. Many deep-sea creatures undertake daily vertical migrations, ascending toward the surface at night to feed in waters richer in plankton and small prey, then retreating to deeper, safer waters during the day to avoid visual predators. These animals might experience pressure changes of the central atmospheres or more during their daily commutes, yet suffer no ill effects. Their bodies are adapted to handle this range of pressure, with cell membranes and proteins that function across the entire range of depths they encounter. Marine mammals that dive to great depths, like sperm whales and beaked whales, face a different challenge. Unlike fish, these animals are air breathers and begin their dives with lungs full of air. Yet sperm whales routinely dive to depths of over 2,000 meters, and Cuvier's beaked whales hold the record for the deepest documented dive by a marine mammal at 2,990 meters. At such depths, the pressure would compress their lungs to a tiny fraction of their surface volume. Yet these animals surface unharmed, ready to dive again. The secret lies in their remarkable physiological adaptations. As a deep diving marine mammal descends, its flexible ribcage allows its lungs to collapse gradually without damage. This collapse actually helps prevent nitrogen from being forced into the bloodstream under pressure, avoiding the nitrogen narcosis that would affect a human scuba diver. The marine mammals stop absorbing oxygen from their lungs long before reaching great depths, relying instead on oxygen stored in their blood and muscles. Deep diving whales have blood with extremely high concentrations of hemoglobin and muscles packed with myoglobin, both oxygen-carrying proteins. A sperm whale's blood can hold 3 times as much oxygen as human blood, and its muscles appear almost black from their extraordinary myoglobin content. These adaptations allow the whale to remain submerged for over an hour, hunting squid in the inky blackness before needing to return to the surface to breathe. When these whales hunt at depth, they also contend with cold. Water temperatures at 2,000 meters hover just above freezing. The whales maintain thick layers of blubber that provide insulation, and their large size helps retain heat. The square cube law works in their favor. As animals get larger, their volume and heat production increase faster than their surface area. A sperm whale loses heat to the cold water more slowly than a small fish would, simply because of its size. Nevertheless, these dives are metabolically expensive, requiring the whales to spend time at the surface between dives, breathing rapidly to replenish oxygen stores and recover from the exertion. The deep-sea environment also poses challenges for sensory systems. In perpetual darkness, vision becomes useless beyond a certain point, though many deep-sea fish have developed extremely sensitive eyes that can detect even the faintest bioluminescence. Some fish have tubular eyes, enormous lenses pointed permanently upward, watching for the silhouettes of prey against the faint surface light. These eyes are so specialized that the fish can see only directly above them. essentially blind to anything to the side or below. Other fish have sacrificed vision entirely, their eyes reduced to useless vestigial organs or covered over with skin. Instead, they rely on other senses, lateral line systems that detect vibrations and pressure waves in the water, chemical sensors that track scent trails, and, in some cases, electrical sensors that detect the bioelectric fields generated by other animals' muscle movements. When these whales hunt at depth, they also contend with cold. Water temperatures at 2,000 meters hover just above freezing. The whales maintain thick layers of blubber that provide insulation, and their large size helps retain heat. The square cube law works in their favor. As animals get larger, their volume and heat production increase faster than their surface area. A sperm whale loses heat to the cold water more slowly than a small fish would, simply because of its size. Nevertheless, these dives are metabolically expensive, requiring the whales to spend time at the surface between dives, breathing rapidly to replenish oxygen stores and recover from the exertion. The deep-sea environment also poses challenges for sensory systems. In perpetual darkness, vision becomes useless beyond a certain point, though many deep-sea fish have developed extremely sensitive eyes that can detect even the faintest bioluminescence. Some fish have tubular eyes, enormous lenses pointed permanently upward, watching for the silhouettes of prey against the faint surface light. These eyes are so specialized that the fish can see only directly above them, essentially blind to anything to the side or below. Other fish have sacrificed vision entirely, their eyes reduced to useless vestigial organs or covered over with skin. Instead, they rely on other senses, lateral line systems that detect vibrations and pressure waves in the water, chemical sensors that track scent trails, and, in some cases, electrical sensors that detect the bioelectric fields generated by other animals' muscle movements. The viperfish takes a different approach to securing oversized prey. This predator, which grows to about a foot in length, has teeth so large that they don't fit inside its mouth. When the viperfish closes its jaws, the teeth angle outward, creating a cage from which escape is nearly impossible. The fish's jaw can unhinge, and its lower jaw can be dropped nearly 90 degrees, allowing it to engulf surprisingly large prey. Its stomach, like that of many deep-sea predators, can stretch to accommodate meals much larger than seems possible. The viperfish also has a light organ on a long dorsal ray that extends forward above its head, which it uses as a lure to attract prey within striking distance. Deep-sea creatures have evolved to waste nothing. When food is encountered, every usable part must be consumed. Hagfish, primitive jawless fish that look like eels, are famous for their role as scavengers. When a dead whale or large fish falls to the ocean floor, hagfish can smell the carcass from great distances. They burrow into the body through any available opening and eat it from the inside out, sometimes consuming so much that they become too full to swim and must tie their bodies in a knot to squeeze excess food out of their digestive systems before they can escape. A single large whale fall can support an entire ecosystem of scavengers for years, providing a bounty of nutrients that sustains life in an otherwise food-poor environment. The Twilight realm, Mesopelagic zone between the sunlit surface waters and the absolute darkness of the deep, there exists a zone of transition, a realm of perpetual twilight, where the last vestiges of sunlight struggle to penetrate before being absorbed entirely. This is the Mesopelagic zone, stretching from approximately 200 meters to 1,000 meters below the surface. Here, in this dimly lit middle depth, more animal life exists than perhaps anywhere else on Earth, a staggering biomass of small fish, squid, and crustaceans that undertakes the largest migration on the planet every single day. The amount of light in the Mesopelagic zone decreases exponentially with depth. At 200 meters, enough light penetrates for human eyes to detect, though it appears as a dim, uniform blue glow coming from above. Colors have long since vanished. Red light was absorbed in the first few meters of descent. Orange and yellow disappeared soon after, leaving only blue and green wavelengths to penetrate this deep. But even this limited light is sufficient for organisms with sensitive vision to detect movement, to see silhouettes, to hunt, and to avoid being hunted. By 600 or 700 meters, light levels have dropped to the point where even the most sensitive eyes can barely detect anything. By 1,000 meters, at the bottom of the Mesopelagic zone, the last photons of sunlight have been absorbed, and true darkness begins. The boundary between light and dark is not sharp, but rather a gradient, and organisms have adapted to every niche within this gradient. Upper mesopelagic predators have large, sensitive eyes that can detect the faintest glimmers of bioluminescence or make out the silhouette of prey against the brighter water above. Prey species have developed counter-illumination strategies, rows of light-producing organs on their bellies that match the intensity of the downwelling light, erasing their shadows. It's an evolutionary arms race. Predators evolve better eyes, and prey evolves better camouflage in an endless cycle of adaptation. Perhaps the most remarkable behavior in the Mesopelagic zone is the daily vertical migration undertaken by countless billions of organisms. Each evening, as the sun sets and darkness covers the surface waters, small fish, squid, krill, and jellyfish begin ascending from the depths. They rise hundreds of meters over the course of an hour or two, entering the surface waters under cover of darkness to feed on the abundant phytoplankton and zooplankton found there. As dawn approaches, they reverse course, descending back into the twilight zone before the rising sun can expose them to visual predators like tuna and seabirds. This migration happens every single day throughout all the world's oceans, involving so many organisms that their collective movement can be detected by ship-mounted sonar. The layer of animals is so dense that early sonar operators thought they had discovered a false bottom to the ocean, a solid seafloor that mysteriously rose toward the surface at night and sank again during the day. They called it the deep scattering layer, and it wasn't until later that scientists realized this apparent seafloor was actually made of living creatures. The scale of this migration is almost impossible to comprehend. Conservative estimates suggest that billions of tons of animal biomass participate in this daily journey, making it by far the largest coordinated movement of animals on Earth. The migration isn't limited to small species either. Larger predators follow their prey into the shallows, creating a cascade of feeding that connects the depths to the surface. Swordfish and marlin that hunt in surface waters by day are found at much greater depths at night, following squid and lanternfish down into the Mesopelagic zone. Even some sharks participate, yo-yoing up and down through hundreds of meters of water, following the deal cycle. Why do these animals undertake such an energetically expensive journey? The answer lies in a balance of risks and rewards. The surface waters are rich in food, far more productive than the deep, thanks to sunlight-driven photosynthesis. But they're also dangerous, full of fast-swimming predators that hunt by sight. By feeding at night, when visual predators are at a disadvantage, mesopelagic organisms get access to abundant food while minimizing their risk of being eaten. During the day, they retreat to depths where there's not enough light for most visual predators to hunt effectively. Essentially, hiding in the darkness until the next nightfall makes it safe to return to the surface. This behavior has profound implications for ocean ecology and even global climate. As mesopelagic organisms feed at the surface and then descend to digest their food, They transport organic carbon from the surface to depth, a process called the biological carbon pump. When they excrete waste or die at depth, that carbon is trapped in the deep ocean rather than being released back to the atmosphere. Scientists estimate that mesopelagic organisms may transport as much as 1 billion tons of carbon annually from the surface to the deep ocean, playing a crucial role in regulating atmospheric CO2 levels. Understanding this process has become increasingly important as we try to predict how climate change will affect ocean ecosystems and carbon cycling. The Mesopelagic zone hosts an astounding diversity of life. Lanternfish, small silvery fish covered in photophores that give them their name, may be the most abundant vertebrates on Earth by weight, with population estimates in the hundreds of trillions. These fish serve as a crucial link in ocean food webs, consuming zooplankton and being eaten by larger fish, seabirds, and marine mammals. Hatchetfish, with their flattened bodies and upward-pointing eyes, drift through the twilight, looking like tiny silver axes. Their bodies are almost entirely compressed in the vertical dimension, an adaptation that reduces their silhouette when viewed from below while providing adequate volume for their organs. Bristlemouths, as mentioned earlier, may outnumber all other vertebrates combined, forming an almost invisible but absolutely essential part of the ocean's ecology. Jellyfish thrive in the mesopelagic zone, their translucent bodies nearly invisible in the dim light. Some species grow to enormous sizes, with bells several feet across and tentacles extending many meters below them. These jellies drift passively with currents, trailing their tentacles like living fishing nets, catching any small animals that blunder into the stinging cells. Other jellies are active swimmers, pulsing through the water with rhythmic contractions of their bells. Many mesopelagic jellyfish are bioluminescent, creating ghostly light displays when disturbed. The crystal jelly, which lives in mesopelagic waters of the Pacific, was the source of green fluorescent protein, or GFP, a molecule that has revolutionized biological research. Scientists who discovered and developed GFP won the Nobel Prize in Chemistry in 2008 for their work. Siphonophores, those bizarre colonial organisms that blur the line between a single animal and a collection of many animals working together, reach their most spectacular forms in the mesopelagic zone. The giant siphonophore Praia dubia can grow to lengths exceeding 130 feet, making it one of the longest animals ever discovered. The colony is composed of thousands of individual zooids, each specialized for a particular function. Some for swimming, some for feeding, some for reproduction, some for defense. Together, they form a long, delicate chain that drifts through the water trailing tentacles, a living drift net that captures prey from a large volume of water. Despite its enormous length, the siphonophore is fragile, easily damaged by rough handling or strong currents. It exists in a delicate balance, maximizing its prey-catching surface area while minimizing the energy needed to maintain its body structure. Squid of various sizes patrol the mesopelagic zone, from tiny species measuring just a few centimeters to larger species approaching a meter in length. Many mesopelagic squid have large eyes relative to their body size, an adaptation for seeing in low light. They also possess chromatophores, specialized cells in their skin that contain colored pigments and can expand or contract to change the animal's appearance. Some squid can cycle through elaborate color patterns, possibly for communication with other squid or to confuse predators. Others remain transparent or pale, relying on invisibility for protection. The abundance of life in the mesopelagic zone has not gone unnoticed by commercial interests. With many traditional fish stocks depleted by overfishing, attention is turned to the enormous biomass of lanternfish and other mesopelagic species. Some fishing companies have proposed harvesting lanternfish for fish meal and fish oil, arguing that the sheer abundance of these fish means they could support a sustainable fishery. However, scientists have raised serious concerns about this idea. Mesopelagic fish grow slowly, mature late, and have low reproductive rates compared to surface fish. More importantly, they play absolutely crucial roles in ocean food webs and carbon cycling. Removing large quantities of mesopelagic fish could have cascading effects throughout ocean ecosystems, reducing food supplies for tuna, seabirds, whales, and countless other species. It could also disrupt the biological carbon pump, potentially affecting global climate. Many marine scientists argue that mesopelagic fish are far more valuable left in the ocean where they support biodiversity and help regulate our climate than they would be as fish meal. The Mesopelagic zone represents one of the least explored and least understood parts of our planet. Despite hosting such tremendous biomass and biodiversity, it remains vastly understudied compared to surface waters or even some parts of the deeper ocean. The difficulty of sampling this zone, combined with the delicate nature of many mesopelagic organisms that don't survive being brought to the surface, has limited our understanding. Recent advances in underwater robotics, including remotely operated vehicles and autonomous underwater vehicles equipped with high-definition cameras, are finally allowing scientists to observe mesopelagic life in its natural habitat. These observations are revealing behaviors and species that were previously unknown, demonstrating just how much we still have to learn about this vast realm of Twilight. Giants of the deep. Colossal and giant squid in the darkness between 1,000 and 3,000 meters beneath the surface. In waters so cold they hover just above freezing, creatures of almost unimaginable size drift through the black. These are the giant squid and colossal squid, the largest invertebrates on Earth. Animals so enormous and elusive that for centuries they existed only in legends, dismissed by scientists as sailors' tales grown exaggerated through retelling. Even today, after being confirmed as real, these animals remain deeply mysterious, glimpsed so rarely in their natural environment that each new observation makes headlines around the world. The giant squid, scientifically named Architeuthis dux, holds the record for overall length among cephalopods. Female giant squid, which grow larger than males, can reach lengths up to 43 feet from their posterior fins to the tips of their two longest feeding tentacles. The body, or mantle, typically measures around 6 to 7 feet long, while those remarkably long feeding tentacles can extend for another 33 feet beyond the animal's 8 shorter arms. These tentacles remain concealed most of the time, coiled tightly near the squid's body, deployed only when prey comes within striking range. When a giant squid attacks, these tentacles shoot forward with explosive speed, their club-like tips equipped with hundreds of powerful suckers that grip the victim and draw it toward the squid's 8 shorter arms and its sharp beak. Despite their impressive length, giant squid are relatively lightweight for their size, with the largest confirmed specimens weighing around 600 pounds. Their bodies appear almost delicate, streamlined for life in the open ocean, with relatively small fins at the rear of their mantles used for slow swimming and steering. The colossal squid, or Mesonychiatuthis hamiltoni, takes a different evolutionary approach to being large. While shorter than the giant squid, at a maximum length of around 30 to 46 feet, the colossal squid is far more massive, far more powerfully built. The largest colossal squid specimen ever captured, caught by fishermen in Antarctic waters in 2007 and now preserved at Te Papa Museum in New Zealand, weighed in at over 1,090 pounds. That makes the colossal squid not just the heaviest squid, but the heaviest invertebrate of any kind currently known to science. Even larger individuals almost certainly exist. Scientists have found beaks in the stomachs of sperm whales that dwarf the beak of the Te Papa specimen, suggesting colossal squid weighing 1,500 pounds or more swim through the Southern Ocean's depths. The colossal squid's body is thick and powerful, its mantle measuring up to 8 feet in length and packed with muscle. Unlike the giant squid's streamlined form, the colossal squid appears robust, almost chunky, built more for strength than for speed. Perhaps the most striking difference between these two species lies in their weaponry. Giant squid arms and tentacles bear rows of suckers, hundreds of them, each ringed with tiny chitinous teeth that dig into prey and hold tight. These suckers leave circular scars on the skin of sperm whales that hunt giant squid, marks that testify to the fierce battles that occur in the deep. Colossal squid, however, possess something far more fearsome. At the tips of their feeding tentacles, where giant squid have suckers, colossal squid have sharp swiveling hooks made of materials similar to human fingernails. These hooks, arranged in 2 rows, can rotate to find better purchase on struggling prey, functioning almost like grappling hooks that pierce flesh and make escape nearly impossible. Combined with rows of smaller suckers between the hooks, this arsenal makes colossal squid formidable predators, capable of tackling large fish like the Antarctic toothfish, fish that can themselves weigh over 200 pounds. The eyes of both species rank among the most extraordinary features in the animal kingdom. Giant squid possess the largest eyes of any known creature, except possibly the colossal squid, with eyeballs reaching at least 11 inches in diameter and pupils measuring over 3 inches across. Colossal squid eyes may be even larger, potentially reaching 12 inches in diameter or more, making them the absolute largest eyes of any animal that has ever lived, larger even than the eyes of the great whales, larger than the eyes of extinct ichthyosaurs and mosasaurs. Why such enormous eyes? In the deep ocean, where even the faintest bioluminescence must be detected at maximum range, large eyes provide crucial advantages. The size of an eye directly determines how much light it can gather, much like how a large telescope can see fainter stars than a small one. Additionally, large eyes have better resolution at long range, allowing these squid to spot potential prey or approaching predators from much farther away than smaller-eyed creatures could manage. Research has demonstrated that colossal squid eyes in particular seem adapted for detecting very large objects moving through the water at considerable distances, specifically large objects like sperm whales. The physics of underwater vision in deep water means that detecting smaller nearby objects doesn't require such enormous eyes, but detecting a massive predator while it's still far enough away to avoid requires exceptional light-gathering ability and resolution. Colossal squid eyes may have evolved primarily as a sperm whale early warning system. Interestingly, colossal squid eyes also possess light-producing photophores located next to the lens, organs that cause the eyes themselves to glow in the darkness. The purpose of these glowing eyes remains uncertain, but they might help illuminate prey or possibly serve in communication with other colossal squid. For centuries, giant squid existed only in folklore and fragmentary accounts. Sailors spoke of kraken, enormous tentacled beasts capable of dragging entire ships beneath the waves. Carcasses would occasionally wash ashore or be found floating dead, but the scientific community remained skeptical that such large squid actually existed as living animals. They assumed the accounts were exaggerations or that the specimens were aberrations, strange individuals from typically smaller species. Not until the mid-1800s did Danish zoologist Geppetta Steenstrup examine enough evidence, particularly distinctive beaks and other hard parts, to conclude that very large squid were real and relatively common in the world's oceans. Even then, no one had seen a living giant squid in its natural habitat. That changed in 2004 when Japanese researchers Tsunemi Kubodera and Kyoichi Mori deployed a baited camera line off the Ogasawara Islands in the North Pacific. The camera captured over 500 images of a giant squid attacking the bait at a depth of 900 meters. The images showed the squid as an active, aggressive predator, not the sluggish drifter some scientists had imagined. When the squid attacked the bait, one of its long, feeding tentacles became snagged on the line. The animal pulled and struggled for 4 hours before finally tearing the tentacle free and escaping, leaving the researchers with the detached appendage as proof. Based on the recovered tentacle, which measured 18 feet long, the scientists estimated the full squid had been at least 26 feet in total length. 2 years later, in 2006, the same research team managed to catch a giant squid on their bait line and bring it to the surface alive, a 24-foot individual that survived long enough to be observed and filmed swimming in a harbor. Then in 2012, Kubadera and his colleagues finally captured high-definition video of a giant squid in its natural deep ocean habitat, nearly 2,000 feet below the surface. The footage showed a silvery, ghostly creature, its enormous eyes reflecting the camera's lights, its tentacles reaching toward the glowing bait. The squid appeared graceful, almost ethereal, pulsing its mantle for jet propulsion, its fins undulating gently, a creature perfectly adapted to its deep, cold world. Colossal squid have proven even more difficult to observe. Found primarily in the southern ocean around Antarctica, they live at depths typically between 1,600 and 6,500 feet, though juveniles sometimes range shallower. The environment they inhabit is among the most inhospitable on Earth. Water temperatures near freezing, oxygen levels lower than in most ocean regions, pressure tremendous, and food scattered across vast, empty expanses. Most of what scientists know about colossal squid comes from dead specimens that have washed ashore, from individuals caught accidentally in fishing gear, or from remains found in the stomachs of sperm whales. Only 9 adult or large juvenile colossal squid specimens had been recovered as of recent years, providing scientists with frustratingly limited data about their biology and behavior. Not until March of 2025 did researchers finally capture the first video footage of a colossal squid in its natural habitat, a monumental achievement given the extreme difficulty of exploring Antarctic deep waters. The footage showed behaviors never before witnessed, providing insights into how these massive animals hunt and move. The video confirmed that despite their bulk, colossal squid are capable swimmers, using their muscular mantles for jet propulsion and their large fins for stability and steering. However, researchers also noted that colossal squid appear to have relatively slow metabolisms, as expected for animals living in such cold water where food is scarce. Calculations suggest that an adult colossal squid weighing 1,100 pounds might require only about 1 ounce of food per day to maintain itself, an extraordinarily low metabolic rate that allows the animals to survive long periods between successful hunts. Both giant and colossal squid face one primary predator as adults, the sperm whale. These deep-diving cetaceans regularly hunt large squid, descending to depths of 2,000 meters or more, and using echolocation to find their prey in absolute darkness. Analysis of sperm whale stomach contents has revealed that squid, particularly large squid, make up a huge portion of their diet in many regions. The battle between whale and squid must be titanic, though it has never been witnessed by humans. Sperm whales often bear sucker scars and hook scars on their skin, circular marks from giant squid suckers and slash-like wounds from colossal squid hooks, evidence that the squid do not submit without a fierce struggle. Some whales carry scars around their jaws and eyes, suggesting the squid fight back desperately as they're being consumed. However, the outcome is rarely in doubt. Sperm whales have evolved specifically to hunt large squid, with teeth only in their lower jaws that interlock to grasp slippery prey, with enormous heads that contain spermaceti oil believed to help with buoyancy control during deep dives, and with the ability to remain submerged for over an hour while actively hunting. The life cycle of these giant squid remains largely mysterious. Scientists believe giant squid reach sexual maturity at around 3 years of age, a remarkably fast growth rate for such a large animal. Females produce enormous quantities of eggs, sometimes 5 kilograms or more, though each individual egg measures less than 2 millimeters in length. Where and how these eggs are laid remains unknown, as no one has ever observed squid spawning behavior in the wild. The tiny hatchling squid, called paralarvae, drift in the plankton near the surface, feeding on microscopic organisms and gradually growing. As they develop, they descend deeper, eventually taking up residence in the Mesopelagic and Bathypelagic zones, where they will spend their adult lives. Giant squid appear to be relatively short-lived, probably dying after their first spawning season, a common pattern among squid. This means individuals might live only 3 to 5 years total, spending almost all of that time growing at an astounding pace, adding many pounds of body weight per month. Colossal squid biology is even less understood. Females produce millions of eggs, over 4 million in one examined specimen, suggesting tremendous reproductive potential. However, the actual reproductive behavior, where spawning occurs, how long development takes, all remain completely unknown. The few juvenile colossal squid that have been studied suggest the young spend time at shallower depths than adults before gradually moving deeper as they grow, a pattern similar to many deep-sea fish species. Growth rates appear slower than in giant squid, consistent with the colossal squid's colder Antarctic habitat, where metabolic processes generally proceed more slowly. The existence of such enormous invertebrates challenges some basic assumptions about body size limitations. In the ocean's midwater regions where food is scarce and conditions are harsh, how do animals grow so large? The answer likely involves multiple factors. Both squid species are highly efficient predators, their large eyes giving them exceptional ability to spot prey in low-light conditions. Their ambush hunting style, remaining motionless until prey comes near, then striking with explosive speed, minimizes energy expenditure between meals. Their soft bodies require less energy to maintain than the heavy skeletons of vertebrates, and they achieve buoyancy through ammonium chloride solution in their tissues rather than through gas-filled swim bladders that would be problematic at great depths. The sheer size itself provides advantages. Larger animals are more difficult for predators to tackle, and they can take larger prey items, accessing food sources unavailable to smaller animals. In an environment where encounters with food are rare, being able to consume large meals when opportunity presents itself and then live off those reserves for extended periods becomes a successful strategy. Despite growing public fascination with these animals, enormous gaps remain in our knowledge. We don't know how long they live, how often they reproduce, what their full range of prey includes, how they interact with members of their own species, whether they're solitary or sometimes social, what factors limit their populations, or how climate change might be affecting them. Each new observation, each captured specimen, each minute of video footage brings new questions as often as it answers old ones. These animals remind us that even in the 21st century, even with all our technology, vast parts of our own planet remain almost as mysterious as the surfaces of other worlds, populated by creatures that would seem fantastical if we encountered them in fiction. Yet they are real, swimming through our ocean's darkest depths, going about their lives unseen and largely unknown. The eternal dark, Abyssal and Hadal zones below. 1,000 meters, below the last traces of sunlight, below the Mesopelagic twilight zone, we enter a realm of permanent night. This is the bathypelagic zone, extending from 1,000 to 4,000 meters, followed by the abyssopelagic zone that reaches from 4,000 meters to the ocean floor, typically around 6,000 meters. In the very deepest places, in trenches that plunge beyond 6,000 meters, we find the Hadal zone, named for Hades, the ancient Greek underworld. These zones together make up the vast majority of ocean volume, and throughout this enormous space, darkness is absolute and eternal. No photon of sunlight has penetrated here since these water molecules last visited the surface, which, for some, might have been centuries ago. The transition from the mesopelagic to the bathypelagic zone is gradual but profound. As the last traces of sunlight disappear, the entire ecology shifts. The vertical migrators that dominate the mesopelagic zone rarely venture this deep. Instead, we find permanent residents, animals that spend their entire lives in darkness, that have never known what sunlight looks like. The water temperature stabilizes at just a few degrees above freezing, varying little whether we're at 1,000 meters or 5,000 meters depth. The pressure continues to increase linearly with depth, adding 1 atmosphere of pressure for every 10 meters. But by this point, all organisms present are so thoroughly adapted to high pressure that further increases make little difference to their biology. Food becomes extraordinarily scarce. Photosynthesis occurs only in the sunlit surface layers, and every depth below that must survive on whatever organic matter sinks down from above. This material, collectively called marine snow, consists of dead plankton, fecal matter from animals living higher in the water column, dead jellyfish, discarded mucus houses from filter feeders, and other organic debris. It drifts downward like a slow-motion snowfall, gradually breaking apart as bacteria and fungi decompose it. By the time marine snow reaches the abyssal depths, much of its nutritional value has been consumed by organisms at shallower depths. What remains is sparse, scattered, and difficult to find. Animals living at these depths must be extraordinarily efficient, capable of surviving on minimal food input, opportunistic enough to take advantage of any food source, no matter how unusual. The most important food falls in the deep ocean are the bodies of large animals that die in surface waters and sink intact to the bottom. A dead whale, for instance, represents a bonanza of nutrition, potentially hundreds of tons of flesh, fat, and bone falling into an environment where food is measured in milligrams per square meter. The impact of a whale fall on the deep ocean floor creates an ecosystem that can persist for decades. Within hours of a whale carcass reaching the bottom, mobile scavengers arrive, drawn by chemicals diffusing through the water. Hagfish, those primitive jawless fish that resemble eels, can smell a whale fall from miles away. They home in on the scent, following the chemical gradient until they find the source. Once they arrive, hagfish burrow into the carcass through any available opening, the mouth, the eyes, the anus, sometimes making their own holes by secreting protein-dissolving slime. Inside the whale's body, they feast, consuming flesh from the inside out. In a few months, dozens or even hundreds of hagfish can reduce a whale's soft tissues to nearly nothing. As the hagfish and other early scavengers finish their work, a second wave of organisms takes over. Crabs and amphipods arrive to pick over the remaining scraps. Polycate worms burrow into the sediment around the carcass, feeding on organic matter that has leached from the body. The whale's bones, now picked clean, become colonized by specialized bacteria that can digest the fats and oils trapped inside the bones, a process that can take years or even decades. These bacteria support their own ecosystem of worms, snails, and other invertebrates that feed on the bacteria or graze on bacterial mats. Eventually, after perhaps 30 years or more, even the bones are consumed, broken down into their component minerals, and dispersed into the environment. The depression where the whale fell may remain visible on the seafloor for longer still, a slight indentation enriched with organic matter, supporting slightly elevated populations of organisms for years after every visible trace of the whale has vanished. Other large food falls provide similar bursts of nutrition. Dead fish, squid, sharks, seals, sea turtles all contribute to the deep ocean food supply when they sink. Even large pieces of driftwood can support specialized ecosystems in the deep sea. Wood-boring clams have evolved the ability to digest cellulose with the help of symbiotic bacteria, allowing them to live on sunken logs. These woodfalls create oases of life on the otherwise barren abyssal plains, small communities centered around a single fallen tree trunk. The abyssal plains themselves cover more than 50% of the Earth's surface, making them the largest habitat on the planet. These vast, flat expanses of seafloor sediment are some of the most featureless landscapes anywhere. The sediment, called ooze, accumulates incredibly slowly, just a few millimeters every 1,000 years in most regions. This ooze consists mostly of the shells of dead microorganisms that lived in the surface waters, rained down over millennia, and compressed into a soft, muddy substrate. The terrain is mostly flat because anything that would create a hill or valley, any seamount or canyon, gets gradually buried under the endless accumulation of sediment. The result is a plain so level that it makes the flattest terrestrial deserts look rugged by comparison. Life on the abyssal plains exists in an environment that seems almost designed to be hostile to living things. Darkness, cold, pressure, and starvation combine to create conditions where only the most specialized organisms can survive. Yet, life persists. Sea cucumbers, relatives of starfish and sea urchins, crawl slowly across the seafloor, vacuum cleaning the sediment for any edible particles. Some species reach impressive sizes, growing to over 3 feet in length. They move at a pace so slow it must be measured in meters per hour, leaving trails in the sediment that can remain visible for months. Small crustaceans called isopods and amphipods burrow through the sediment or scurry across it, feeding on bacteria and detritus. Brittle stars, relatives of starfish with long, slender arms, spread their arms to trap any particles drifting past in the weak currents. Sea pins, colonial organisms related to corals and sea anemones, anchor themselves in the sediment and extend their polyps to feed. Fish life in the abyss is sparse but highly specialized. The grenadiers, or rat-tail fish, are among the most common fish families on the abyssal plains. They have large heads and eyes, tapering bodies that end in a long, rat-like tail, and swim slowly just above the bottom, using sensitive chin barbels to detect prey buried in the sediment. Tripod fish have taken an unusual approach to life in the abyss. They possess 3 elongated fin rays, 1 on the tail and 2 on the pelvic fins, that they use as stilts to stand on the seafloor, facing into the current with their pectoral fins spread wide to sense prey items drifting past. This allows them to feed without expending energy on swimming, a crucial adaptation where food is so scarce that every calorie must be conserved. The Hadal zone, below 6,000 meters, presents even more extreme conditions. Trenches that reach these depths are relatively rare, scattered around the world's oceans, like isolated islands of extreme environment. The Mariana Trench in the Western Pacific, the Tonga Trench in the Southwestern Pacific, the Philippine Trench, the Japan Trench, the Peru-Chile Trench off South America's west coast, the Puerto Rico Trench in the Atlantic all plunge into the Hadal depths. Each trench hosts its own suite of organisms, often species found nowhere else on Earth. The trenches are so isolated from each other, separated by thousands of miles of shallower seafloor, that there is little mixing of species between them. This isolation has led to high levels of endemism, with each trench containing its own unique fauna. At Hadal depths, the pressure becomes almost unimaginable. At 11,000 meters in the Challenger Deep, the pressure exceeds 1,080 atmospheres, over 15,000 pounds per square inch. Yet amphipods thrive here, small crustaceans that look something like shrimp but belong to a different order. Hadal amphipods can be quite large for their group, some species reaching lengths of over 6 inches. These amphipods are scavengers, feeding on any organic matter that settles into the trenches. When researchers deploy baited cameras in Hadal trenches, swarms of amphipods often appear within hours, sometimes hundreds or thousands of individuals converging on the bait. Their ability to detect food falls from great distances and converge rapidly suggests that food is so scarce in the trenches that they must be constantly searching, ready to travel significant distances when opportunity presents itself. The deepest dwelling fish ever reliably recorded is the Hadal snailfish, observed and collected at depths exceeding 8,000 meters in several trenches. These fish are extraordinary creatures, almost entirely unlike any shallow water fish in their appearance and biology. They lack scales, their bodies covered instead in a gelatinous transparent tissue that appears almost ghostly. They have no gas-filled swim bladder, maintaining neutral buoyancy through other means. Their skeletons are barely mineralized, more cartilage than bone, flexible and compressible rather than rigid. Their cells are packed with TMAO to protect their proteins from pressure damage. These fish are active predators despite their soft appearance, hunting small crustaceans and worms in the trench environment. The fact that fish can exist at these depths at all seems remarkable, until we realize they represent the culmination of millions of years of evolution, every aspect of their biology fine-tuned for survival under conditions that would instantly kill most other organisms. Below about 8,500 meters, fish disappear entirely. This appears to be a hard limit imposed by biochemistry. Even TMAO cannot adequately protect cellular proteins beyond this depth, and fish simply cannot function. However, other organisms persist. Sea cucumbers have been photographed at the bottom of the Challenger Deep, nearly 11,000 meters down, slowly crawling across the sediment. Amphipods and other crustaceans continue to be found at the very greatest depths. These animals have additional adaptations beyond what fish possess, though the exact nature of these adaptations remains an area of active research. The Hadal trenches remain among the least explored environments on Earth. Only a handful of human-occupied descents have ever been made to full Hadal depths, and robotic vehicles capable of withstanding the pressure and operating in such challenging environments are expensive and rare. Each expedition to these extreme depths returns with surprising discoveries, new species, unexpected behaviors, communities of organisms living in areas that were thought to be barren. The trenches had their own geology, their own chemistry, and their own ecology, functioning almost as separate worlds contained within our ocean. In some trenches, sediment accumulates differently than on the abyssal plains. In others, rocks from Earth's mantle are exposed, minerals that normally never interact with seawater. These exposed rocks can interact with water to produce hydrogen gas through chemical reactions, providing potential energy sources for bacteria and, through them, for entire food webs independent of sunlight-derived nutrition, somewhat similar to hydrothermal vents, but operating through different chemistry. The deepest places on Earth continue to yield secrets, With each advance in technology, with each new expedition, we learn more about how life adapts to extremes, how ecosystems function under the most challenging conditions imaginable, and how much diversity and complexity exists even in places that appear uniformly hostile to life. Human exploration and discovery. The story of humanity's gradual understanding of the deep ocean mirrors our exploration of any frontier. For most of human history, the deep sea remained as unknown as the surfaces of other planets, accessible only through imagination and rare fragments of evidence that washed ashore or became entangled in fishing gear. Ancient peoples living near the coast knew the shallow waters intimately, but had no means to explore beyond the depth that divers could reach, holding their breath, perhaps 30 or 40 meters at most. The deep ocean, everything below that, existed as pure mystery. The first systematic attempts to study deep ocean depths began in the late 1800s with the advent of research vessels equipped to deploy sampling equipment on long cables. The HMS Challenger expedition from 1872 to 1876 represented a watershed moment in oceanography. This British research vessel spent 4 years circumnavigating the globe, stopping at frequent intervals to measure ocean depths, collect water samples, and deploy nets and dredges to capture specimens from the seafloor. The expedition's findings revolutionized scientific understanding of the ocean. They demonstrated that life existed at all sampled depths, contradicting the prevailing theory that nothing could live below about 600 meters. They mapped ocean floor topography, discovering underwater mountain ranges and trenches. They collected thousands of new species, many of them bizarre and unexpected. The expedition's scientific reports filled 50 thick volumes, establishing the foundation for modern oceanography. But actually seeing the deep ocean, directly observing its inhabitants in their natural environment, would require technology that didn't exist in the 19th century. The first steps toward direct observation came in the early 20th century with the development of tethered diving bells and helmeted hard-hat diving suits that allowed humans to descend somewhat deeper while still breathing air pumped down from the surface. These systems rarely exceeded 100 meters in depth due to the physiological limitations of breathing compressed air and the practical difficulties of managing long air hoses. The breakthrough came with the invention of the bathysphere in the 1930s by American naturalist William Beebe and engineer Otis Barton. This steel sphere, just 4.5 feet in interior diameter with thick quartz windows, could be lowered on a cable to depths far beyond what diving suits could reach. In 1934, Beebe and Barton descended to 3,028 feet, about 923 meters, in the bathysphere off Bermuda. Beebe's radio broadcasts from depth, describing the strange fish he saw outside the windows and the profound darkness beyond, the reach of their lights, captured public imagination and provided the first vivid, real-time accounts of deep ocean life. However, the bathysphere's cable tether limited its range and made it dependent on good weather conditions. The next evolution came with the bathyscaphe, pioneered by Swiss physicist Auguste Piccard in the 1950s. Unlike the bathysphere, which hung from a cable, the bathyscaphe was a self-propelled free-diving vessel, essentially an underwater balloon that used a large gasoline-filled float for buoyancy and iron ballast weights that could be dropped to ascend. This design allowed the bathyscaphe to dive much deeper than cables lowered vessels, while giving pilots control over their ascent and descent. Auguste Piccard's bathyscaphe Trieste, later purchased by the United States Navy, would become the vehicle that carried humans to the deepest point on Earth. On January 23, 1960, Jacques Piccard, son of Auguste, and U.S. Navy Lieutenant Don Walsh climbed into the pressure sphere of the Trieste and began their historic descent into the Challenger Deep. The descent took nearly 5 hours, as the bathyscaphe slowly dropped through increasing pressure and darkness. At certain depths, they stopped to check their systems and confirm the sphere wasn't being compromised by the immense forces pressing against it. As they approached the bottom, around 35,000 feet deep, they heard a loud crack that they feared might indicate a failure in the pressure sphere. They later discovered the sound came from a crack in one of the external plexiglass windows, not critical to their safety. At 200 feet from the bottom, they released some ballast to slow their descent, landing gently on the seafloor at a depth later calculated to be 10,916 meters below the surface. What they saw through their small viewing port astonished them. Against all expectations that the deepest depths might be completely lifeless, they reported seeing a flatfish, perhaps a flounder or sole, lying on the sediment and what appeared to be a shrimp swimming past their viewport. These observations have been questioned by some scientists who argue that true fish cannot survive at such depths due to pressure-related physiological constraints. Whatever Picard and Walsh actually saw, their observations made it clear that the deepest ocean was not the sterile, lifeless void some had imagined. They remained at the bottom for 20 minutes before releasing ballast and beginning their ascent, which took 3 hours and 17 minutes. The achievement was so difficult and the specialized equipment required so expensive that more than 50 years passed before another person would make a similar journey. James Cameron's solo descent in 2012 aboard the Deep-Sea Challenger represented both a technological leap forward and a continuation of the spirit of exploration that motivated Picard and Walsh. Cameron, a filmmaker known for his interest in deep-sea exploration, worked with engineers to design a vertical torpedo-shaped submersible specifically optimized for deep trench exploration. Unlike the Trieste gasoline-filled float, the Deep-Sea Challenger used syntactic foam, a material made by embedding tiny glass spheres in epoxy resin, providing buoyancy while being able to withstand enormous pressure. The vehicle carried advanced cameras and scientific sampling equipment. Cameron's descent on March 26, 2012, took 2 hours and 37 minutes, reaching the bottom of the Challenger deep at a depth of 10,898 meters. He spent 3 hours exploring the seafloor, filming high-definition footage, and collecting samples. The environment appeared more barren than he expected, covered in fine sediment with few obvious large organisms, though smaller creatures certainly inhabited the mud. Equipment problems prevented him from completing all his planned activities, but the expedition proved that deep ocean exploration was becoming more accessible. The most recent phase of deep ocean exploration has been led by Victor Vescovo, a private investor and retired naval officer who commissioned the construction of the DSV Limiting Factor, a 2-person submersible designed for repeated dives to full ocean depth. Between 2018 and 2020, Vescovo and his team completed the 5 Deeps expedition, reaching the deepest point in each of the world's 5 oceans: the Atlantic Ocean's Puerto Rico Trench, the Southern Ocean's South Sandwich Trench, the Indian Ocean's Java Trench, the Pacific Ocean's Malloy Deep. Vescovo personally piloted dives to each of these extremes, sometimes with scientists or other observers as passengers. The Limiting Factor has proven to be a reliable, reusable deep ocean vehicle, completing dozens of dives to Hadal depths and enabling scientific research that would have been impossible with earlier, one-off expedition vehicles. These human-occupied descents have provided invaluable first-hand observations, but much deep ocean exploration now relies on robotic vehicles. Remotely operated vehicles, or ROVs, connected to surface ships by tether cables that carry power and communication signals, can stay submerged for days at a time, collecting samples and recording video without putting human pilots at risk. Autonomous underwater vehicles, or AUVs, operate without tethers, following pre-programmed routes or making their own decisions based on sensor input. able to cover large areas and conduct surveys in regions too dangerous or remote for other approaches. These robotic systems have discovered hydrothermal vent fields, mapped underwater mountains and canyons in high resolution, and documented deep-sea ecosystems in unprecedented detail. One of the most sobering discoveries from recent deep ocean exploration has been the prevalence of human-caused pollution even in the most remote depths. Plastic debris has been found in the Mariana Trench, at the bottom of the Hadal zone, far from any human presence. Microplastics, tiny fragments of degraded plastic less than 5 millimeters in size, have been detected in the tissues of organisms collected from the deepest trenches. Pollutants, like persistent organic chemicals, industrial contaminants that were banned decades ago, are nevertheless present in Hadal organisms, having been transported there through food webs and ocean currents. These findings demonstrate that nowhere in the ocean is truly pristine, that human impacts have reached even to places where humans have almost never been. The future of deep ocean exploration will likely involve increasingly sophisticated autonomous systems, vehicles that can explore for months at a time without human intervention, using artificial intelligence to make decisions about where to go and what to sample. Deep ocean observatories, permanent installations that monitor ocean conditions and ecosystems over years or decades, are being deployed in strategic locations. New submersibles are being designed that can reach full ocean depth while carrying more powerful sampling equipment and better sensors. Despite these advances, the deep ocean will remain challenging to explore, expensive to reach, and difficult to study. Yet the discoveries waiting there, the species we haven't yet found, the ecosystems we haven't yet documented, the geological processes we don't yet understand, justify the effort. The deep ocean is not separate from the surface ocean or from the atmosphere above it. It plays crucial roles in global climate, in nutrient cycling, in the carbon cycle that regulates atmospheric CO2 levels. Understanding the deep ocean is essential for understanding how Earth's systems function as a whole. And so our journey through the depths concludes, having descended from the Twilight zone through regions of total darkness, having encountered organisms adapted to pressures that would crush most living things, having seen how life persists in places that seem designed to be lifeless. The deep ocean reminds us that our planet is more diverse, more complex, and more surprising than we often imagine. Even now, in an age of satellites and global communication, vast regions of our own world remain unexplored, inhabited by creatures we haven't named, functioning through processes we haven't yet understood. There is something profoundly humbling and simultaneously exciting about that realization. Closing. If you've enjoyed this journey into Earth's deepest waters, if learning about the remarkable adaptations of deep-sea life has brought you a sense of wonder, consider supporting this channel by clicking the like button and subscribing for more explorations of science and nature. Your support helps create more content like this, long-form deep dives, if you'll pardon the pun, into topics that deserve more than superficial treatment. The ocean covers more than 70% of our planet's surface, yet we've explored less than 5% of it in any detail. Every expedition reveals new species, new behaviors, new mysteries waiting to be solved. By supporting science education and exploration, you're helping ensure that future generations will continue to unlock the secrets of our remarkable planet. As you drift towards sleep tonight, perhaps you'll carry with you images of the deep ocean's mysteries, bioluminescent creatures twinkling like stars in liquid darkness, the dance of hydrothermal vent communities thriving on chemical energy from Earth's interior, the silent passage of giant squid through black water, the slow rain of marine snow nourishing life in the abyss, the crushing pressure of the deepest trenches where life somehow persists against all odds. The deep ocean is always there, beneath the waves, hidden from view but utterly essential to the functioning of our world, a frontier as alien as any we might find among the stars, yet right here, covering most of our home planet's surface. Sleep well, knowing that even as you rest, countless organisms are going about their lives in the depths, perfectly adapted to their extreme environments, part of ecosystems we're only beginning to understand, living proof that life finds ways to flourish, even in the most challenging conditions imaginable. Thank you for joining this expedition into the deep. Until next time, may your dreams be as deep and mysterious as the ocean itself.